I'm going to talk about the trigonometric half-angle identities. These are sometimes referred to as the trigonometric power reduction identities. I will assume that you're familiar with the trigonometric double angle identities as well as the trigonometric Pythagorean identities. If any of those are unfamiliar to you, I would invite you to watch the necessary videos. So what I'm going to do is first list the identities, then I'm going to show you where they come from, then I'm going to use them in a couple of examples. So here are the trigonometric half-angle identities. So the sine squared of alpha over 2 is equal to 1 minus the cosine of alpha all over 2. The cosine squared of alpha over 2 is equal to 1 plus the cosine of alpha all over 2. The tangent squared of alpha over 2 is equal to 1 minus the cosine of alpha all over the sum 1 plus the cosine of alpha. Notice that on the left sides you have squared functions, and on the right side you have all expressions in terms of the cosine of alpha. Now, to derive these three identities, I'm going to start with the following trigonometric double angle identity. The cosine of 2 alpha is equal to the cosine squared of alpha minus the sine squared of alpha. Now, the identity is still true if I replace alpha everywhere with alpha divided by 2. If I do that and simplify, I will get the following. Okay, so I basically just cut all the angle measures in half. Now I can write the right side of the last equation, the last identity, in alternate forms by using the trigonometric Pythagorean identity. So the cosine of alpha is equal to, if I replace the cosine squared of alpha over 2 term, I get this. If I replace the sine squared of alpha over 2 term, I get 1 minus the cosine squared of alpha over 2. So again, I use the trigonometric Pythagorean identity for both of those substitutions. Now I can solve for the sine squared of alpha over 2 in terms of the cosine of alpha, and I can also solve for the cosine squared of alpha over 2 in terms of the cosine of alpha by using the last two versions. All right, so if I do that, if I solve for the sine squared of alpha over 2, I will get the following. This is, I'm using the second to the last identity. So go ahead and move the terms around yourself and see that indeed you get 1 minus the cosine of alpha all over 2. The last black identity, if I solve for the cosine squared of alpha over 2, I will get this. Okay, so move the terms around in the last black identity if it's not clear how I arrived at the second blue identity. Okay? Now for the identity with respect to the tangent function, I'm going to derive it by using the following. The tangent squared of alpha over 2 is equal to the sine squared of alpha over 2 all over the cosine squared of alpha over 2. And now I can use the two blue identities that I just derived. Okay, and the 2's in the two denominators cancel, and so I'm just left with the following. All right. Now, let's use these identities in a few exercises. So how would we determine the cosine of pi over 8 without a calculator? Now, pi over 8 is not a special angle measure, but pi over 4 is. So why don't we use the following identity. The cosine squared of alpha over 2 equals 1 plus the cosine of alpha over 2. And let's replace alpha with pi over 4. So that'll give the cosine squared of pi over 8 equals 1 plus the cosine of pi over 4 all over 2. And that's equal to 1 plus the square root of 2 over 2 all over 2. And I can double every term in the numerator and denominator, and that'll give 2 plus root 2 over 4. But that's the square of what we're looking for. Now, because the angle measure we're focusing on, pi over 8, is an acute angle, the cosine must be positive, so we don't have to consider minus the square root of the bottom, just plus the square root of the bottom. So the square root of 2 plus root 2 over 4, and we can take the square root of 4, that's 2, so that leaves us with 2 plus root 2, the square root of 2 plus the square root of 2 all over 2. Okay? Now, let me try this another example. How about the sine of pi over 8? So I will use the following identity. I will replace alpha with pi over 4. So that'll give 1 minus the square root of 2 over 2 all over 2. Double all the terms in the numerator and denominator. That'll give 2 minus the square root of 2 over 4. And we are interested in the positive square root of the bottom because pi over 8 is an acute angle, so the sine value will be positive. And so we're left with the square root of 2 minus the square root of 2 over 4. And we can take the square root of 4, that's 2. So the final answer is 2 minus the square root of 2, the square root of 2 minus the square root of 2 all over 2. All right. Now, would you try to do an example? Would you please try to find the sine of 15 degrees without a calculator? So I'll go ahead and work it out as well. So I will use the following identity. I'm going to replace alpha with 30 degrees. So the cosine of 30, we can do that without a calculator. That is the square root of 3 over 2. Now I will double every term in the numerator and denominator. And once again, we have the square of what we're looking for. Now, because the sine of 15 degrees has to be positive, because 15 degrees is an acute angle, we will only consider plus the square root of the bottom. And the square root of 4 is 2, so we can pull that out of the radical. And so we have the square root of 2 minus the square root of 3 all over 2. Okay? Now, here's a different type of exercise. Can you prove that 2 times the cosine squared of theta over 2 minus the cosine theta is equal to 1? So pause the video and try to do that now, please. So I'll go ahead and work it out as well. So I'm going to use the following identity to replace the squared term. So I'm going to replace alpha with theta, and so I'm going to have the left side therefore is equivalent to 2 times 1 plus the cosine of theta all over 2 minus the cosine of theta. If I distribute the 2, I get, and let me also, when I distribute the 2 into the numerator of the fraction, let me also split that fraction up into 2 fractions. So 2 times 1 gives 2. When I divide that by 2, I get 1. And then 2 times cosine theta is 2 cosine theta. When I divide that by 2, I get just cosine of theta. And the cosine theta cancels with the minus cosine theta. So I just have 1, which is equal to the left side. And so we've successfully set out to prove what we wanted to prove. Okay? What about this one? Can you prove that 2 times the cosine squared of theta over 2 times the secant of theta is equal to the secant of theta plus 1? So pause the video and try to prove that assertion. Okay, so I'll go ahead and work it out as well. So I'm going to again use the identity that the cosine squared of alpha over 2 is equal to 1 plus the cosine of alpha over 2, and I'm going to replace alpha with theta. And so the left side of the original assertion is equivalent to 2 times 1 plus the cosine of theta over 2 times the secant of theta. And as before, the 2's cancel. So I have, let me now distribute the secant of theta into the sum. So I'm going to get the secant of theta plus cosine of theta times the secant of theta. But the secant of theta is the reciprocal of the cosine of theta. So that product is just 1. So the left side is equal to the secant of theta plus 1, which indeed is equal to the right side, which is the secant of theta plus 1. Okay? And so let's close with one involving the tangent function. So can you prove that the tangent of alpha over 2 is equal to the sine of alpha over 1 plus the cosine of alpha? All right, pause the video and try to work that one out now. Okay, so I'll go ahead and work it out as well. So I will use the following identity. The tangent squared of alpha over 2 is equal to 1 minus the cosine of alpha all over 1 plus the cosine of alpha. And let me multiply the top and bottom by 1 plus the cosine of alpha. Okay, and so on the top I'm going to have Now that is the difference of two squares pattern, so I'm going to have 1 minus the cosine squared of alpha in the numerator. You can expand that out and convince yourself that indeed that's what it's equivalent to. And then on bottom I'm going to have 1 plus the cosine of alpha squared. And the numerator is equal to, using the trigonometric Pythagorean identity, that's equal to the sine squared of alpha all over 1 plus cosine of alpha, that whole sum squared. Okay, and now the tangent of alpha over 2, if I take, because the last line gave me the square of what I'm of the left side. So the tangent of alpha over 2 is equal to plus or minus the square root of the right side of the last line. And so plus or minus the sine of alpha over 1 plus the cosine of alpha. And one way to see whether it's the plus or minus choice is to pick a random value for alpha. So, for example, if alpha was, let's say, 10 degrees, then the left side is positive, so the right side has to be positive. The sine of 10 degrees and the cosine of 10 degrees are all positive. So we would want to discard the negative solution. And so therefore, the tangent of alpha over 2 is equal to plus the sine of alpha over 1 plus the cosine of alpha, which is equal to the right side that we in the original assertion. All right, and so we've established